Hey there, physics class. I'm going to go through our topic of electric fields. Going to go through some notes, work through a couple different calculations. Hopefully at this point you've had a good chance to look over the simulations that we've assigned so that you can see the electric field and how it is generated by positive charges and negative charges, and how the electric field is related to the electric or Coulomb force. So the first thing I want to make sure that we remember about this electrostatic force and why it's so, I guess, unique. Really, there's only a few different forces that we associate with fields, is that the electrostatic force can be felt from a distance. This is a long-range force. We've talked about gravitational force already. That's another example of a long-range force. So we like to think about the electrostatic force as a long-range force and explain it in terms of the electric field. We'll think about a field as surrounding a charged object. And it's the way in which a charged object is going to affect or modify the space around itself. So this electric field is going to surround a charged object. And depending on whether that's a positive charge or a negative charge, we can describe the nature of that field. We generally use arrows to represent our electric field. And we think about what would happen, well, if I place a charged object right here, maybe a positively charged object, I can use these arrows to represent the direction in which that positively charged object would be pushed. Basically, we're relating it to the electrostatic force. If I want to measure the electrostatic force, I can use an electric field to do that. The strength of our electric field is going to equal the Coulomb force at any point in space divided by the charge of the object I place there. So if I put a positively charged object Q right there, and this charged object experiences a force when it's placed there, then our electric field is the ratio of the force experienced divided by the charge of the object we've placed there. Our units that we use for measuring electrostatic force, electric field, are newtons per coulomb because it's force over charge. Now, if we want to think about this, this measurement here, electric field, it's also a vector quantity. It has to be a vector quantity because force is a vector quantity. And if we think about the direction of that electric field, it's always going to be in the same direction as force on a positive charge. So what we think about is if I were to place a positive charge in an electric field, which direction would that charge be pushed? Well, another thing to think about here is that it really depends on whether the charge that's generating the electric field is a positive charge or a negative charge. So if I think about what happens around a proton, if I bring a second charged particle in here near this proton, it's going to be pushed away. If I bring a negatively charged particle near this proton, it's going to be pulled inward. When we think about electric field, we're thinking about what would happen to a positive charge only. We're focused on the positive charge, so we have basically a standard that we can compare from one charge to another. So if I put a positive charge over here, it's pushed outward by this central positive charge. Now let's change things up. Now, instead of having a positive charge in the center here, let's switch it for a negative charge. So if I place a negatively charged particle here, and now I'm going to bring in my positive test charge, because remember, we're always thinking about the direction on some positive charge. This positive test charge is going to be pulled inward because it's going to be attracted to that negative charge in the center. If I put a positive charge over here, this positive charge is going to be pulled inward. So if we're thinking in general about what the electric field should look like around, say, just some general positive charge, it's always going to be directed radially outward around a positive charge. Positive charges push other positive charges away. But if we're looking at a negatively charged object, say an electron or a group of electrons, the electric field around an electron is always going to be directed radially inward because it always pulls positive objects inward. So that's our representation of an electric field, basically showing which way is an object can be accelerated if it's a charged object, a positively charged object placed in the vicinity of this field. All right, so that's our basics of the electric field. And we've got our equation here. So let's try relations with the electric field. All right, first thing to take a look at, a positive test charge of 5 times 10 to the negative 6 coulombs is in an electric field that exerts a force of 2 times 10 to the 4th newtons on it. What's the magnitude of the electric field at the location of the test charge? So again, the electric field tells us about what a positive charge, what happens to any charged object that's placed in the space. It's telling us our force per unit of charge. So if I want to figure out the electric field here, electric field is equal to the force divided by our charge that's experiencing that force. So our electric field is going to equal our force magnitude, I've got that right here, 2.0 times 10 to the negative 4th newtons, all divided by the amount of charge. And this is 5 times 10 to the negative 6, 5.0 times 10 to the negative 6 coulombs. When you put this into a calculator, make sure you've got parentheses here so that we divide by that 10 to the negative 6 rather than multiply by it. It's a really common error when you're putting numbers into a calculator. Our electric field strength should end up being about 40 newtons per coulomb. One thing I want to point out here, so that's our final answer. Notice I'm just getting the magnitude of it. I'm not so worried about the direction here. I really don't have a coordinate system associated with this problem. So even though the electric field is a vector quantity, I need more information and maybe a picture to go with this problem if I want to talk about the direction of the electric field for this question. I want to talk about this 5.0 times 10 to the negative 6 coulombs. This is a pretty standard, amount of charge. A lot of times when we're dealing with charges, we're talking about 10 to the negative 6 coulombs because 1 coulomb of charge is actually a ridiculously large quantity of charge. But I want to just focus in on 10 to the negative 6 because we're commonly going to see this as written in terms of a unit conversion using our powers of 10. So 10 to the negative 6 could also be written as micro coulombs. So another way of writing 5 times 10 to the negative 6 coulombs would be 5 microcoulombs. Now when we put it into our equation and we do this division, we probably want to have this in the scientific notation right there so that our answer, because our answers for electric field are usually in newtons per coulomb. But if you see this symbol micro here, it means 10 to the negative 6. All right, so I think that's it for that problem. I'm going to show you another example. A positive charge of 3 times 10 to the negative 7 coulombs is located in an electric field of magnitude 27 newtons per coulomb. What's the magnitude of the force acting on this charge? So if I know this is how much electric field I have, and I know that I want to place this charge in the electric field, that charge is going to experience a force. It's going to get a push from this field. It's going to accelerate as a result. So we're again going to use our equation that electric field is equal to force divided by charge. But now we're solving for something different. It says, what is the magnitude of that force? So we're going to have to solve for F. I'm going to rearrange the equation first and rewrite this as F equals Q multiplied by E. Again, we're looking for the magnitude of this force. We're not so worried about directions in this case. The magnitude of this force should equal the charge, which is 3 times 10 to the negative 7 coulombs, multiplied by our electric field, 27 newtons per coulomb. You can go ahead and see if you can do that multiplication. I think you should find you get something like 8.1 times 10 to the negative 6 newtons for the magnitude of that force. Check my math on that one. I've got two significant figures because I'm multiplying two things together with two significant figures. And this force, I mean, it's a really small amount of force. But we're talking about probably a small charged object here, and so it could accelerate quite a bit. Because don't forget, we still have to, if we want to relate to acceleration, we'd still need to relate to net force equals mass times acceleration. I'm not asking you for the acceleration of this particle, and I'm not giving you the mass of that particle. But remember that this still connects back to all of the mechanics stuff we've done before. The Coulomb force is no different really than the tension force or the friction force. It's just a new kind of force. The one special thing about it is that it's a long-range force, which is why we get to talk about fields now. All right. I have for you just another quick discussion here, and that has to do with electric fields from point charges. So before we had just talked about general electric fields, but we can talk specifically about the electric field generated by a single positive or a negative charge or anything that's spherically symmetric, a uniform charge sphere. So we can calculate the field that's produced by this system. And the equation we use actually looks a little bit like the Coulomb's law equation. It's derived directly from the Coulomb's law equation. Our electric field for a spherically symmetric system or a point charge is equal to K times Q, all divided by D squared. Notice that all we've done is we've chopped out one of the charges from our Coulomb's law. This Q here is the charge that's producing the field. So when I place my positive charge here out in space, it's going to modify the space around itself, and it's going to generate an electric field. And what this equation allows me to figure out is how strong that electric field that this positive charge generates is. And it allows me to say, well, if I place another charge near it, if I bring a positive test charge in here later, what's going to happen to that charge? Which way is it going to be pushed? How strong is that push going to be? Basically, when I place a positive charge somewhere out in space or a negative charge, I'm going to modify the space around that object. This equation will allow me to predict how a single charge modifies the space around itself. So let's figure out what the electric field is when we're at a position that's 1.6 meters to the east of a point charge with this amount of charge. All right, so I've got a positive point charge here, and this positive point charge is going to generate an electric field around itself that pushes outward. But we're interested in what happens at a distance that's 1.6 meters away from that positive charge. The question is, what's happening at this point here? Maybe you know from this picture, and knowing that this is a positive charge, that our electric field should be pointing in this direction. It points outward. Because if I were to drop a positive charge right here, it's going to be pushed away from that central positive charge. I don't need to have a positive charge there in order to talk about the electric field, but it helps us to visualize what's going to happen and what's going on here. So we're going to use our equation for the electric field for a point charge. It's K, Q, all over D squared. If you remember from before, this K value is our Coulomb's law constant. It's the same for every time we use it, it's 9 times 10 to the ninth Newton meter squared per Coulomb squared. It's a fundamental constant of nature. So we can use that value in our equation here. Make a little bit more room. E is equal to the Coulomb constant, 9 times 10 to the ninth Newton meter squared per Coulomb squared, multiplied by the charge. We're interested in this central charge because it's creating the electric field. So the charge on this object, positive 7.2 times 10 to the negative 6 coulombs. And let's divide by the distance we are away. 1.6 meters, and that value should be squared. Go ahead and see if you can do that calculation. I think what you should find is that our electric field has a value of 2.5 times 10 to the fourth in this region, and we can actually take a look at the units here, try to figure out what our units should be for electric field. I've already told you what the units should be for electric field, but let's verify it using our equation. And the way we verify that is basically through dimensional analysis. Let's see what units cancel out, because I've got a whole bunch of units in here. Notice that I've got meters squared in the denominator and meters squared in the numerator. Let's get rid of those. Notice that I have coulombs here and Coulomb squared in the denominator in my Coulomb constant K. I'm going to get rid of one of these coulombs in that squared value. And then I've got nothing else to cancel newtons. So I'm left with newtons divided by coulombs. And those are our units, remember, for electric field. Electric field is the amount of force that 1 coulomb of charge would experience if we place it in this field. So if I put a 1 coulomb point charge near this other charge that's described, it's going to receive 2.5 times 10 to the fourth newtons of force. That's a pretty big amount of charge and a pretty big force. Usually we're looking at things with a much smaller amount of charge on them. But that's what this unit means. We're showing force per charge. All right. So let's see. We'll do another example. If we're thinking about the electric fields from point charges. The electric field is 0.25 meters. I'm sorry, the electric field that is 2.5 or is 0.25 meters from a small sphere is 450 newtons per coulomb. What's the net charge on the sphere? Now, one thing that you'll notice is this is directed inwards towards the sphere. That means that if I have my charged sphere here, the electric field points inward. That actually tells you the sign of the charge right away. If we have electric field lines pointing inward, we must have a negative charge on this sphere. All right, so I know that right away. What I can do now to solve for the rest of this, to solve the numerical quantity, is say that my electric field is equal to K times Q all over D squared. I'm trying to solve for Q. I'm trying to find the charge. So the first thing I'm going to do is I'm going to multiply both sides by D squared. And then I've got D squared times electric field equals KQ. I want to get Q by itself, so let's divide by K on both sides. Great. Now my equation looks like this. Q equals D squared E, all divided by K. Doing all that stuff first before I sub in any of the numbers can help you keep organized and make sure that you don't lose anything in your scientific notation as you're moving values around. So I'm going to clear some space here so that I can now sub in those values and figure out what Q is. Because remember we said Q is equal to D squared. All right, what's my distance? It's 0.25 meters squared. Multiplied by the electric field strength. That's 450 newtons per coulomb. All of that divided by K. K in this problem is 9 times 10 to the ninth Newton meter squared per Coulomb squared. It's a constant. It gets to be the same value every single time. All right, so now we're solving for that charge, and we find that well, remember, it's a negative value. It's negative 3.1 times 10 to the negative 9 coulombs. 10 to the negative 9, if we were to think about using our SI prefixes, we could also call 10 to the negative 9 coulombs the same as a nanocoulomb. So we can rewrite that if we want and say that Q is equal to negative 3.1 nanocoulombs. All right, so let's go through another example. Again, using that equation for our electric field for a point charge. Our electric field equation, K Q over D squared. All right, so how far from a point charge of 2.4 times 10 to the negative 6 coulombs must you place a test charge in order to measure a field of magnitude 360 nanocoulombs? All right, so let's figure out what values we have. I've got an electric field of 360 newtons per coulomb. So electric field is 360 newtons per coulomb. Our charge involved, 2.4 times 10 to the negative 6 coulombs. The question asked me, how far? That's probably my distance. And then, of course, there's the Coulomb constant K, 9 times 10 to the ninth Newton meter squared per Coulomb squared. Those are my 4 different variables here. I'm solving for D, so I'm going to try to get D by itself. In order to do that, I also want to get it out of the denominator, so I'm going to multiply both sides by D squared. And then my equation looks like this. D squared times E equals K times Q. I'm almost there. Let's divide by E on both sides. And now my equation looks like this. D squared equals KQ over E. That's great, but it's still not solving for D, the distance. If I've got D squared and I want the distance separation, I actually have another step to take. That next step is the square root. So all of this stuff that I'm going to multiply and divide here, my final answer is achieved by taking the square root of that. So D equals the square root of KQ over E. So let's go through and plug all of those numbers in. So there is our equation. So we find that E is equal to the square root of 9.0 times 10 to the ninth multiplied by, actually, I'm going to need a little bit more room here, I think. D equals the square root of 9 times 10 to the ninth Newton meter squared per Coulomb squared multiplied by 2.4 times 10 to the negative 6 coulombs, all divided by our electric field, 360 newtons per coulomb. And make sure all of this stuff here ends up in your square root. You should find that distance to be equal to 7.7 meters when you calculate that out. All right. One more page here. I'd like to talk about drawing the electric field and what a picture of the electric field looks like. We've done a little bit of this electric field mapping already, but I just want to give you some quick summary information here. So when we're trying to picture or show the electric field, it's done with what we call field lines. And those field lines map the field. This idea of how to picture or represent an electric field, which is how a charged object affects or modifies the space around itself, was originally proposed by Faraday. Michael Faraday, famous physicist, 1800s, did a lot of really cool stuff, and we'll talk more about Michael Faraday as we go through the rest of this course. But if we want to talk about the direction of the field lines, those give an indication of the types of charge. So they always point away from positive charges and towards negative charges. So here I've got a positive charge and that positive charge at the middle. We would draw the electric field lines pointing outward from it. And if I have a negative charge, negative charges have electric field lines that point inward. A positive charge is acting like a source of electric field lines. They emanate outward from a positive charge. Whereas a negative charge acts like a sink or a spot for field lines to land. If we have a complicated system of multiple charges, the pictures and the mapping system still holds. Our positive charge is a source for field lines, and our negative charge is a sink or a landing spot for those field lines. But one thing also to note is the density of the electric field lines gives us a visual indication of the strength of the field. So for example, right here where I've got lots of field lines really close together, that's a really strong electric field. If I put a test charge here, it's going to get a big push. But if I put that test charge out further away, if I put that test charge out here, notice the spacing of the field lines out here, they're a lot more separated, and that's going to be a weaker force at that point. Just counting the electric field lines around a charged object will give us some indication of how strong that field is as well. If we count how many field lines land on this negative charge, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, versus the field lines that leave this positive charge, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That tells you that this positive charge and this negative charge, this one right here and this one right here, they may be opposite, one positive and one negative, but their magnitudes are the same. Because physicists use the number of field lines leaving a charged object to give an indication of the strength of that charge. All right, so I hope that helped give you a better picture of electric field lines, what they are, how they work, how we can use them, and how we can do some calculations with them. So I'm going to stop there for right now, physics, and good luck with your homework problems, and let me know if you have any questions about them.